Welcome back to our series on multivariable calculus. In this episode, we're going to talk about the cross product. The cross product is the second of two ways to multiply vectors. The first was the dot product, sometimes called the scalar product, and today we're going to talk about the cross product, often called the vector product. And the reason why is the cross product produces a new vector. Let's take a look at the derivation of the cross product based on what it does. First, we're going to define two vectors, vector A at A1, A2, A3, and vector B at B1, B2, B3. In addition, I'm going to define a third vector. I'll just use this temporarily to define the cross product. It'll be vector V, and it will be at coordinates V1, V2, V3. And in essence, here's what we want to do. We want to derive a vector that is perpendicular to two given vectors. That's one of the things the cross product does for us. So we're going to look at its derivation by forming a new vector v, which is simultaneously perpendicular to A and B. Well, in order for vectors to be perpendicular, their dot product must be 0. So that becomes our criteria. First, that A dotted with V is equal to 0. That will guarantee that V is perpendicular to A. Well, let's look at what that dot product would be. A dotted with V would produce A1 V1 plus A2 V2 plus A3 V3. Correspondingly, I want V to also be perpendicular to B. So we need to evaluate this dot product as well, A dot V, and set it equal to 0. And this dot product is B1 V1 plus B2 V2 plus B3 V3. Well, as you can see, we're going to run into an issue right off the bat. Even if we knew A1, 2, and 3 and B1, 2, and 3, substituting those into these two equations and having solutions for those equations still produces three variables with only two equations. And unfortunately, that means I can't solve the system exactly. What I'm going to have to settle for is one of the many solutions that V could be perpendicular to A and B. See, with the proper choice, we can actually choose one that has some interesting implications. Okay, in solving this system then, I want to eliminate the third term, basically the one that contains V3. And in order to do that, I'm going to multiply the entirety of equation 1 by B3. And the entirety of equation 2 by negative A3. And you can see what that'll do. That will make these two terms identical, but of opposite sign. And when I add them, the third term will disappear. The first two terms, though, when I sum them, they'll still add up to 0. And let's take a look at what that is. So this will still be equal to 0. And I'll draw a horizontal line to represent the sum, but I'm basically going to add together the product of B3 and these two terms with negative A3 and these two terms. I'm also going to do some factoring. So first, the V1 terms. It will be A1 times B3 minus A3 times B1. And that will be times V1. That's the first column. Let's do the second column. That will be A2 B3 minus A3 B2. And that will all be times V2. And that's it for these two equations. If I add them together after the multiplication by these, I eliminate the third column, and this is what I get. Well, this is still an unsolvable equation. It's one equation with two unknowns, V1 and V2. But what I'm going to do now is make a choice. I'm going to choose to say that V1 and V2 are going to take on these values. That is, this will be the value of V2, and this will be the value of V1. And I know by making that choice, I'm making this equation true, which means this is a valid solution to the system. So let's go ahead and write those solutions down. Now, these can't be exactly equal to this term in parentheses being V2 and this term in parentheses being V1, because then they wouldn't add to 0. One of them has to be negative. I'm going to choose for the V2 term to be negative. So that's going to make V1 equal to what's in these parentheses, A2B3 minus A3 B2. And it's going to make V2 equal to the negative of this set of parentheses, A1, B3 minus A3, B1. Now, if I go further, if I take these solutions for V1 and V2, and I substitute them back into either one of these first two equations, I will get the following for V3. V3 will end up being equal to, it'll be A1, B2 minus A2, B1. And that turns out to be a pretty valid solution to this problem, which is, let's find a vector that is simultaneously perpendicular to A and B. Well, V with these particular components, based on the components of A and B, will satisfy that result. If I were to substitute these back in to V and then take the dot product, they'll indeed turn out to be 0 when dotted with both A and B. So let's write out the entirety of it. In addition, I'll show you the symbol for the cross product. If we take A cross B, with A and B being defined by the vectors above, then the vector it produces will be A2, B3 minus A3, B2. That'll be its x component. Negative A1, B3 minus A3, B1. That will be its y component. And A1, B2 minus A2, B1. That will be its z component. So there it is. There's the cross product between two vectors. Now, it's a little bit more involved than the dot product was. The dot product was a fairly easy device to memorize, so you didn't really need any mnemonic device or skill in order to produce a dot product. The cross product, though, lends itself to a little bit more complexity. Not only does it produce three components, but those components each have their own little formula. Well, let's talk about a couple of ways that you could produce the cross product just as easily as you do the dot product. What I'm going to show you is a matrix mnemonic device for identifying the terms of the cross product. And that device starts with the three unit vectors, I, J, and K. Those are the three column headings. And then in the next two rows, I'm going to put in the first vector in the cross product, vector A, which is A1, A2, A3. And the final row will be the second vector in the cross product, B1, B2, and B3. And then we'll draw vertical lines around both sides. Later on, we'll talk about what this actually is. We're actually going to find the determinant of this 3x3 matrix. But we'll save that for later in the course when we really look at linear algebra. For right now, all we're interested in is borrowing this as a nice mnemonic device. The one thing I have to add to this before I show you this little technique is the idea that the center term of this as a result of the choice we made up here is always negative. And so let's add that negative right now by putting it on the j hat term. So now that we've done that, we've put in the negative that came as a result of our choice. And now the rest is pretty easy. One of the reasons it's called the cross product is that you actually take the product in a cross pattern. Let me show you what I mean. Imagine taking I and blacking it out, that is, erasing it from this matrix together with its column and its row. So there's no I here, and there's no JK, and there's no A1, B1. All that's left is these four terms. Well, we do the following. I take A2 times B3, the downward diagonal, and I subtract B2, A3, the upward diagonal of what remains when I remove the row and column of the first term. So I is blocked out, and I take A2, B3 minus B2, A3. And notice that's exactly what this first term is. And that's all in the I hat direction. So it tells me that it's in the x direction. Well, let's go further. I'm going to block out the j row and the j column, but I'm going to retain the negative. And what remains, of course, is A1, B1, and A3, B3. So the second term is going to be negative, open parentheses, A1 times B3 minus B1 times A3. And that's all in the j hat direction. And you'll notice that's exactly what this term is, A1, B3, B1, A3. And then finally we do the same thing for the third column. We block out the K column and the row, and what remains is A1, B2 and B1, A2. So this will be plus, and then the final term is A1, B2 minus B1, A2. And that's in the K hat direction. So this is a very easy mnemonic device for reconstructing this formula. If you don't have any problem seeing the pattern in this formula, this will always give you the vector cross product. But if you find this difficult to apply, or you have to keep writing it down and referencing it, keep in mind you can always construct this 3x3 matrix, and the pattern of pulling out the solution from it is pretty straightforward. Okay, so now that we know how to obtain the cross product, let's look at a couple of other aspects of it. One is its magnitude. The magnitude of the cross product, A cross B, would mean putting this entire mess through the Hyperpythagorean theorem. That is, we'd square this and add it to this squared and add it to this squared and put it under the square root. And I promise you, it will end up forming quite a bit of an algebraic mess. If you're interested, you can actually watch a video that derives that from beginning to this end by following the link above. But let's just cut to the chase. The magnitude of the cross product will be the magnitude of vector A times the magnitude of vector B times the sine of the angle between them. So it's defined in a very similar way as the cross product. The magnitude of the vectors times the cosine of the angle between them would give you the dot product. The cross product simply uses the sine of the angle. What this does, however, keep in mind, is it only gives you the magnitude. This will be a scalar quantity. It will only be the size of the cross product. The actual cross product is provided by this formula or by taking the determinant of this matrix. So keep in mind that while the dot product was a scalar and taking the shortcut through the cosine angle gave you the same answer as the formula, that is not true for the cross product. One is a vector and the other one is simply the magnitude of that vector. Well, let's talk about what the cross product actually gives you. We already know one of the things it gives us because it's how we defined it. The cross product gives us a vector that's always perpendicular to the two vectors we took the cross product of. So the answer to A cross B will be a vector that's perpendicular to A and B. But what about its magnitude? Well, let me show you that. If I draw a vector A and B in a plane, and I put the angle between them, it will form the corner of a parallelogram. Let's complete the parallelogram. So A moved over here and B moved up here will form a parallelogram. Well, the area of that parallelogram is actually the size of the cross product. So that A cross B, the magnitude of that cross product will be the area. And of course, there's a couple of ways to calculate the area of a parallelogram. One of the easiest ways drops a perpendicular line to its base and calls that the height. And of course, the area of a parallelogram is the height times the base. Now, the height won't be the same as the length of a side, but it is related to the sine of the angle. And that's why the magnitude of the cross product is always AB sine theta. A times the sine of theta will actually be equal to this height, and that times B will provide the area of the parallelogram. One of the interesting things is we used dot products to project one vector onto another, and we're actually going to be able to use cross products to figure out the distances between points, lines, and planes. And that comes as a result of this perpendicular line right here. Because the height is perpendicular to this side, it's going to allow us to find the minimum distance between points and lines and points and planes. Now, the cross product has lots of other applications. One of the biggest, it comes from physics in torque and rotational dynamics. The second major application for the cross product in physics is it helps us with magnetism and electromagnetism. Here in linear algebra, the cross product is going to do a couple of things for us. It's definitely good at finding things that are perpendicular to planes, but it's where it really shines is finding the minimum distance between objects. Well, there's the cross product. There's how to calculate it, a mnemonic device that helps you remember it, and then one of its applications, that it finds the area of a parallelogram defined by the two vectors. We'll talk more about the cross product as we engage in our next two lessons on three-dimensional planes and lines.